Hello everyone, welcome to In 5 Minutes. In this video we are going to see the next problem on differentiation under integral sign. So this is our question. Show that this integration is equal to root pi by 2 e raised to minus 2a. So we have to solve this integration, but we will solve this integration by using DUIS. So here we have constant a, so we call this term as I of a, which will be integration of 0 to infinity e raised to minus x square plus a square upon x square into dx. So this is our I of a. Let's call this equation 1. Now we have to apply DUIS. So DUIS with respect to constant, that is a, that is this term will be I dash of a derivative integration 0 to infinity partial derivative with respect to a of this term, which will be e raised to minus x square plus a square upon x square into dx. Okay, so now this term will become integration 0 to infinity. We have to take the derivative of this term with respect to a, so x square will remain constant. So derivative of e raised to minus some constant into variable is e raised to minus same thing into derivative of this term. Okay, so here also we are going to apply the same formula. So e raised to minus x square plus a square upon x square will remain as it is, and derivative of this bracket, so x square is constant because we are derivating with respect to a, so x square will be constant, so derivative will be 0, plus 1 upon x square is also constant, and derivative of a square will be 2a into dx. Okay, and this minus sign, so we will have integration 0 to infinity, this minus sign I am taking here, e raised to minus x square plus a square upon x square into 2a upon x square dx. Now we have to integrate with respect to x. So 2a is constant now, so we can take 2a outside the integration. You will get I dash of a minus 2a integration 0 to infinity e raised to minus x square plus a square upon x square into 1 upon x square dx. So now we have to perform this integration. So this is a very complex integration, so we put a by x equal to t, then x will be a by t, then dx will be minus 1 upon t square dt. Since we are changing the variable, our limits of integration will also get changed. So here we write initial variable and here we write new variable. X is going from 0 to infinity. When we put x equal to 0, we get t equal to infinity. When we put x equal to infinity, we get t equal to 0. So our new integration will be minus 2a integration of infinity to 0 e raised to minus x square, that is this square, a square upon t square, plus a by x square, that is t square, into 1 upon x square dx. So 1 upon x square will be 1 upon a square into t square, and dx is minus a by t dt. Okay, so this t and t will get cancelled, 1a from here and 1a from here will get cancelled. So we have minus 2 integration of infinity to 0, and I am taking this minus sign inside integration, so integration limits will get swapped. So we have integration 0 to infinity e raised to minus t square plus a square upon t square into t dt. Here it is t square, so this t square and this t square will get cancelled, we have dt. Now if you see, this term is exactly matching with this term, only variable here is x and the variable here is t. So we get minus 2 integration of 0 to infinity e raised to minus x square plus a square upon x square into dx by change of variable theorem. So if we have the similar equation, instead of t we can write x. Okay, so this is how we change the variable. So this term, if you see, is nothing but this term, which is I of a. So I dash of a is nothing but minus 2 I of a. Okay, so remember this term. So we get I dash of a. Now we have to find I of a. We want this I of a value. So now what we are going to do, we are going to integrate on both the side with respect to a. Why we are integrating with respect to a? Because here we have taken the derivative with respect to a, so we will integrate with respect to a only. So we will have I dash of a minus 2 integration of I of a. So I am taking this I of a in the denominator. I will have I dash of a upon I of a integration minus 2 integration of d of a. Okay, so consider this part.